This video is the first in a series of lectures dealing with motion in a plane, an XY plane. I show a path followed by some object undergoing motion, an arbitrary path. At some point, the point at which we begin our observation of this particle is moving in a plane, a two-dimensional flat surface. The magnitude of the velocity of the object, in other words, the speed of the object, is v naught. That velocity vector has an x component and a y component. We symbolize the x component of the initial velocity with a subscript x after the naught symbol. Likewise for the initial vertical velocity or y velocity. Later, as time goes by, the particle will be elsewhere and will have in general a different velocity, which we can symbolize as v. That velocity vector has two components, an x component and a y component. Notice the absence of the subscript naughts, the zeros. They only apply to the initial values of those components. Now the example I'll work next, and most of the problems that we'll work in this chapter, will put to use only a limited set of motion equations. In our previous discussion of vertical motion and horizontal motion, there were a list of 5 equations. I show you just 2 equations for each component of motion. There are the motion equations that apply to the x part of the motion. Those are the equations which have symbols that are subscripted with x's. We have 2 such equations for the x part of the motion. And we have 2 equations where there are y subscripts that deal with the y part of the motion. All of the problems in this chapter, including the problem example I will work here, and all of the other problems, will only put to use a limited set of the equations that you've already been exposed to. This is a good thing, and I've shown those equations here. The most important equations are these shown here. To a lesser degree, these are important also, but know these equations and believe that these equations are quite similar to the ones that you saw for vertical motion or horizontal motion. All right, let's work a sample problem that has nothing to do with this particular general path that I asked you to look at. We imagine that our object is initially at the origin of our coordinate system, our two-dimensional coordinate system. It's at the origin 0, 0, when we first look at the particle. The x component of our object's acceleration is 0. That means the velocity along the x direction will not change. Whatever it is, it always is. But the object does have an initial x velocity. v naught subscripted x is the x component of the initial velocity, which I declare is 10 meters per second. As for the y part of the motion, the y acceleration is 4 meters per second. That means with each passing second, the y component of the velocity increases by 4 meters per second. Further, know that the y component of the initial velocity is negative 3 meters per second. What we want to know is, after 5 seconds have gone by, how far is the object from its initial location, which I've already said is always going to be at 0, 0, at the origin of our xy coordinate axes. Well, we'll find the answer to this question by finding the separate x and y coordinates of the object when t equals 5 seconds. I'll put to use the equation here, substituting for Vox, or V v naught x, as we prefer to say, 10, and then times 5, and the rest of it is a 0 because a sub x is 0, no acceleration along the x-axis. This works out to 50 meters. That's the x-coordinate of the object at this later instant in time. Now let's get the y-coordinate. It's the same equation as shown here, except everywhere you see an x, put a y. Substituting for v naught y, -3, and then the time period t is 5 seconds. And you have 1/2 times the y acceleration, which is 4 meters per second, times 5, but it's squared. 5 squared is 25, times 2 is 100, divided by 2 is 50, subtract 15. The y-coordinate of our particle at the end of this observation period is 35 meters. And so I show where this object is later on our xy coordinate plane. That's the starting location at 0, 0. That's its later location at x equal to 50, y equals 35. And so we have a right triangle here whose leg height is 35 and whose base width is 50. And we use a theorem of Pythagoras, the square root of the sum of the squares equation. Final result is that our particle, after 5 seconds have gone by, will have moved a distance of 61.03 meters. All of the problems that I'll work in the rest of this chapter will deal with a special type of motion in a vertical plane called projectile motion. In such a case, our work is made simpler by the fact that for projectile motion, a sub x, as is the case in this example, is always 0. So the horizontal velocity, the x velocity of our projectile, will never change. It's further made simpler by the fact that the y acceleration of our objects in every single example we will work in Chapter 3 is a certain number that I'll give to you later. That number for the y acceleration will be the same for all problems, so there's less for you to do and less for you to remember. Well, that's something you can look forward to. If looking forward to physics lectures is something you commonly do,